Hi, welcome to Concept Based. I'm John Hepworth, and this one's for Year 11 advanced students. We're still in the working with functions part of your syllabus, and we're in a really strange part of that topic. It's called circles and semicircles. Now, when I say strange, I mean it's weird that it's here because circles actually aren't functions, but parts of circles are. What am I talking about? Well, let's do what Mr. Hepworth always says, and let's draw a graph. So what do you know about circles and their equations and their graphs? You hopefully know this, that x squared plus y squared equals r squared is actually the equation for a circle. Hopefully you know that from a conceptual basis on how Pythagoras' theorem works and how you could draw a triangle anywhere within a circle. But that's not what this question's about. So we're not going to go too deep into it. I want to go into the part that makes this a function or not. So we've covered already what makes a function a function. We know that a vertical line test will tell us, and if we do a vertical line test, this thing fails. It's not a function, it's a relation. Now, and we can call this one-to-many. So in the case of one-to-many, it's not a function. So why is this in this part of the syllabus? Well, in another part of the dot points, it talks about the semicircles. Now, some of the semicircles are functions, so let's have a look at what of those are. So if we go and look at the top half of the circle, we would have a function. Here it is, here, passes the vertical line test. If we did the bottom half of the circle, same situation, we have a function. But what about if we did a side of the semicircle? Well, once again, we're back into this relation situation. So we need to be able to identify which ones are which ones are functions and which ones aren't. So how do we get these functions or relations out of this circle equation? All we want to do, first of all, is just make y the subject. So we're used to having y the subject in most of our equations. So that seems fine. So let's just get that x squared away from it. And then we take the square root. And we get y equals plus or minus the square root of r squared minus x squared. And it's this plus or minus bit out the front that actually still makes sure that we get the entire circle. So what would happen if we don't have the whole plus or minus out the front? What if it was just a plus out the front, which we don't write? We just write it as the radical. So whenever you see a radical like this, it just means the positive part of the radical. It doesn't mean plus or minus. So if we're just looking at the positive part of the radical, the y values have to be positive because the square root is always going to give us a positive value. And so the y values are only positive above the x-axis. So we're going to get a semicircle that looks like this. But what if we had the negative part? Well, then we're only going to get negative y values and we get that bit. So how do we get the left-hand side or the right-hand side? We do that by making x the subject. And you could imagine that if I would have made x the subject earlier, it's exactly the same as if we made y the subject. We would have ended up with this. And then we've got this plus or minus. Now, sometimes students mess this up and they're like, is it the left-hand side of the semicircle or the right-hand side of the semicircle? So you have to think to yourself, well, what are we talking about here? We're talking about x values being positive or negative. If the x values are positive, then we must be talking about this part of the semicircle because this is where the x values are positive. And therefore, if we had this negative, we must be talking about this part of the semicircle. Now, it's interesting that I've drawn this because this is from the question. Intersect x equals negative root 4 minus y squared. So we need a 4. Okay, so let's change it a little bit. Let's put a 4 in here, which is obviously 2 squared. So this is going through at 2 and at negative 2 and at negative 2. And we're intersecting that with the function y equals x. Okay, y equals x is a function. It passes the vertical line test. It goes through and we get an intersection point here. Now, at some point in the future, you do graphing techniques and you do have to estimate answers from your graphing techniques. So you could guess what sort of decimal position that this is at. But that's not what we are going to do today. Today we're going to do it algebraically. So let's go and do this algebraically. So we've got x equals minus root 4 minus y squared. Now I'm not going to write y squared. I'm going to make a substitution from this equation. Y is equal to x. So I'm actually going to write 4 minus x squared, not y squared. Okay, so now I'm going to solve this equation. So I square both sides and I get x squared equals 4 minus x squared. I add x squared across and I get 2x squared equals 4. Divide by 2 and then take the square root. Now, whenever I take the square root, the plus or minus appears again. Okay, so x could be plus root 2 or it could be minus root 2. But if I go back to my actual graph, I don't have any positive x solution to this. I just have this negative x to the solution. So therefore, it must just be the negative root 2. But how do I say this, or what am I even talking about here? Well, what we can say here is that x does not equal positive root 2 because as x is less than 0, and we know that from this equation back up here, x, root 4 minus y squared has to be positive, and then we're taking the negative of that. So x has to be negative. So therefore we can discount x equaling positive root 2. And so x equals negative root 2. Now, sometimes students stop here. They think, I found it. I found the solution. Yes, you solved for x, but the question is actually saying, find the point of intersection. So we have to find the point. Lucky for us, there's a really easy equation to substitute into, y equals x. Let's substitute into that and get y equals, well, x is negative root 2. So that's going to make y equal to negative root 2. And we're going to end up with this point being the point of intersection on our graph. And that all makes sense because we do get a negative y value for where this negative x value is going to be. Now, be aware, these types of questions, the HSC loves to have multiple choice in these types of questions because how do we know what's what? They might say it intersects at positive root 2, and you've got to work out, well, how do I know whether it's negative or positive? Maybe they say it intersects at both. And you'd be like, yeah, we don't discount any, they're all there. So you need to know whether you are discounting them or not, whether you are taking the positives or not. Now, there might be a question in your mind that's saying, hey, Mr. Hepworth, how did we actually get both x answers when we shouldn't because it didn't exist? And the reason is this step here. Look what we did. We squared both sides of this equation. And when we squared both sides of this equation, we actually lost a little bit of information. We lost this negative information or positive information there. If we were talking about the other side of the semicircle, it would have been a plus there. And if we would have squared a plus, we would have gotten positive. But we had negative there, and we squared the negative and we got positive. So we get positive in both situations. So the algebra actually loses information in this step. And now it doesn't know whether I was talking about the left-hand side of the equation or the right-hand side of the equation. So it served up algebraically both answers for me. It served up that positive root 2 also because it didn't know which side of the semicircle we were on. So that's why you need to go and check your solutions and see which ones make sense. And again, as I always say, if you draw a picture first, the chance of checking your algebra and making sure that it's correct is significantly improved. So of this multiple choice question, if it was one, there's our answer, negative root 2, negative root 2.